All right. Hello, everyone. I'm Ryan, and I'm presenting the Oreboot status update with Sheng from Intel. All right, so in this talk, you'll learn what Oreboot is, some of the firmware challenges which are involved, how we designed it, some challenges specific to the programming language we used called Rust, and some of its new targets, including AMD ROM, RISC-V, and FSP-based systems. And finally, we'll talk a bit about how you can get involved in this project. So what is Oreboot? So here's a brief, incomplete history of other firmware projects like U-Boot, Linux Boot, Oreboot, Nerf, Linux Boot, UBMC, Slim Bootloader. And what a lot of these have in common is they're written in a language, C, a language that's been used for probably 30, 40 decades. Sorry, 40 years. And what we're trying to do in Oreboot is trying something completely new, writing firmware in a safer language, a more modern language. It was made in the last decade, and which can solve some problems that you might encounter in C. And Oreboot is more than just Coreboot without the C. It's a downstream fork of Coreboot, so a lot of the source code is based off of Coreboot, so it's also GPL v2. There's no C code, but there's some small pieces of assembly here and there. So for example, initializing the stack pointer in the beginning or jumping from real mode to protected mode is in assembly. So it's very useful for those tricky bits. But one of the main goals of Oreboot is not to have an exhaustive list of drivers or to do netboot or disk boot or any of that stuff. The main goal is to jump into a Linux kernel so that we could use Linux boot to do all the fancy stuff with network drivers and disk drivers. So Oreboot is actually fairly simple. It just, for the platforms where you need to, it just initializes memory, ACPI tables, and jumps Linux as fast as possible. So the policy is we avoid closed source blobs wherever possible, but we have some exceptions. And it's currently all open source, Oreboot itself. Okay, so this is a very brief overview of how it's designed. So it begins with the boot blob, like I said, all assembly. It does a single print, welcome to Oreboot, and it does a very, very preliminary CPU initialization, sets up cache as RAM. It's a fair bit of assembly code, but the next stage, the ROM stage, is completely written in Rust. It executes from Flash. It uses very little memory. All of it is stack-based, so there's no like malloc, no heap. And the main purpose is to initialize RAM on systems where you have to initialize RAM. And as soon as that's complete, we jump to the payloader stage, which is where we generate those ACPI tables. And it has the one job of running the payload. So it doesn't do netboot, USB stacks, anything with lots of complexity. And then the fourth stage, which is Linux boot, the user mode typically implemented in Go has all the facilities to perform a netboot or disk boot, and it's very flexible and secure and very robust. So this is a bit of Rust code, and this is kind of the model we're using for our what we call drivers. We don't have an extensive set of drivers like we mentioned previously, but we have some drivers, for example, relating to serial or some basic operations such as that. So each driver has a init function, read and write function. In the model of Rust, you want to avoid mutability as much as possible. So it's a p read, so it's a positional read. So the driver itself doesn't contain a cursor. So there's some elements of Rust which drive our decision making like that. And you'll see here, for example, strings, the all static. All right, so this is a list of drivers we have. So we have memory drivers, so that's reading and writing to physical RAM. PL011, NS15, all those drivers, the serial drivers for various platforms. We have an MMU driver for controlling the MMU, initializing that. For Sci-Fi, we have a SPI driver. Then we also have, which is interesting, a number of virtual drivers. And the one that we find the most useful is the union driver, what we call the driver of drivers. So for example, if you want to write to 2 serial ports at the same time, instead of writing to both of them, you use the union driver to take 2 serial drivers, and one write to the union driver will write to both of them. So it essentially contains a list of drivers, and it propagates the write call through to both of them. So it's fairly useful if you want to write to multiple serial ports, or you want to write to a serial port and a memory console log as well at the same time. It has a lot of different usages, as well as slice reader, section reader. Those are used for creating kind of windows into the memory address space. For example, we use it in a device tree parser extensively, and a few other cases. So like I mentioned, this is the console, or the driver of drivers in action. You can see here we have a list of UART, so we have multiple UART drivers. This is on the ARM platform, and you can see here one writes to all 5 of them at the same time, and it's fairly simple as well. And one of the really neat things, or very useful things about REST, is the standard library. They have a subset which is designed for embedded systems, so it doesn't have any dependencies on an operating system. It's called the core library, and it contains a number of useful utilities, for example, printf. So we don't have to implement our own printf function. You'll see here there's a format args, and it's completely capable of formatting that string, converting the 7 to a string and whatnot. So we get printf for free. Unlike almost every other C program out there, we didn't have to re-implement printf. And this makes it very easy to add and remove new drivers. So the flash layout we use something similar to CBFS called DTFS, where it's described as a device tree. The main benefit of this is, at least for Linux, we can pass the device tree to Linux, and there's already a driver within Linux to convert that device tree into the sys file system to access it. So from Linux, we could access contents of the flash layout through this DTFS. So it's kind of an interesting idea. It's easy to parse. We have a parser inside of REST for a device tree, which doesn't use any heap allocation. It's purely stack based, and we could constrain the stack size. So we guarantee that it will always never run out of memory. All right. So in terms of REST, like I mentioned before, we don't use any dynamic allocation. And the really nice thing about the LLVM compiler, which REST uses, is there's a feature which prints the total stack requirements that your program requires. This depends on not using any recursion or complex function pointer calls. But if you have a fairly normal program, it will tell you how much stack space your program uses, and then you can look at how much space you have in cache's RAM, and you can say, yes, it will fit, guaranteed. There'll never be a stack overflow because it's pre-computed exactly how much stack size your program will use. So it's a pretty nice property to guarantee. We have to design a program in a specific way, never to allocate anything on the heap, and in fact, we don't really have a function to do that. But so far, we've been completely capable of that. All right, another thing in REST that we're looking into is using coroutines. So a big advantage of this is faster boot time. So we notice in many cases, booting is, especially for servers, it's bounded by I/O, especially UART prints. So oftentimes, like a few thousand UART prints might take like a fraction of a second, because the CPU is essentially polling. Like unless you have interrupt-based firmware, which many firmware implementations are not usually polling, the CPU is just burning many cycles on polling. So instead of having interrupt-based I/O, which is pretty difficult, even like in the like it's kind of a slippery slope to becoming a full kernel, which we want to avoid. The alternative in REST is REST supports essentially something sort of like coroutines, and it has built-in support in the language called async await. So the idea is instead of polling, you would jump to a different coroutine, execute their code there, and then jump back to the UART coroutine, and you kind of jump back and forth. So it's still a single thread, but there's multiple stacks of execution. It's still something we kind of have to look into more. But it's an interesting idea, and it says REST provides some safe mechanisms to do so. All right. So next I'll cover the targets which Oreboot supports. So first, back earlier last year, we implemented Oreboot for ARM in QEMU using the virtual target, and this was fairly simple. It was only a couple of days, and we probably don't have enough time for the demo, but essentially it prints "Welcome to Oreboot," and the device tree was hard-coded at the time. The next target we had was the High5 Unleashed. This is a RISC-V platform. It had 4 hearts, which means 4 cores. It's Linux capable. So for Oreboot, we booted into what was called M mode, so machine mode. We booted Linux in machine mode, which required a special patch to Linux config RISC-V M mode. We were also able to boot OpenSPI, which allowed booting Linux normally in S mode. And for the High5 Unleashed, the memory initialization was completely open source, and we were able to natively implement the memory initialization in pure REST code, which is pretty unique. Many platforms, the memory initialization is closed. All right, so on to x86. So originally the plan for Oreboot was to never ever have any binary blobs. But of course, that would be impossible for x86 because pretty much all popular x86 platforms now require it. So we made kind of a list of ground rules where we will say we will allow it if we comply with these 6 rules. And they're pretty comprehensive. For example, the number 6, so any compromises to the language safety features of REST have to be explicitly stated. So for example, if we have an ABI to communicate with that binary blob and that ABI passes back a string pointer, there's no guarantee that that string pointer actually points to valid memory. So we'd have to explicitly document that was one of the safety features which gets compromised. Anyway, so this was the first x86 port for Oreboot, the AMD Rome server CRB. So what it has is a PSP, platform security processor. So this is an ARM processor which boots before the main x86 boot core. The memory init happens by the PSP. So once you hit the first instruction of x86, the memory is already initialized. So PSP itself is proprietary and locked down, so we wouldn't be able to do that in Oreboot. However, since everything after, since the first instruction of x86 and after memory has been initialized, it's fairly simple to do a complete Oreboot port for that. But what is missing? So we need to generate the OCP tables. We have to somehow interface with the PSP to determine what the memory layout is and what else is missing. So a big chunk which is missing is a number of MSRs which are undocumented, which needed to be set in order to initialize or in order for Linux to operate properly. So we were looking at it, we were looking at various documentation, and we asked a number of people, but no one really knows, or we knew no one who knew where the documentation was. So we devised a solution in order to determine which MSRs had to be set in order to boot Linux. So essentially, Ron took an implementation which already booted into Linux and dumped the MSRs at their current states at different points during that program. And he was able to bisect and zero in on where those undocumented MSRs were set. And that basically did the trick. So after that work, we set all those values from inside of Oreboot, and Linux boots fine now, with a few caveats. So one caveat is we can only do basic programs, like we could run a shell or a few simple commands. More complex things like PCI and networking don't quite work. So as you can tell, this is still a fairly, I wouldn't say it's ready for like production use, of course. So like things like SMP are still in the works, IO APIC. But the significance behind this is the first implementation for the AMD realm, which is OSF compliant from the first instruction of x86 onwards. So all of the UEFI and the proprietary x86, which is not compatible with OSF, has been removed. So this is technically the first OSF compliant solution for AMD realm. All right, so I'm going to hand it off to Sheng to talk about OpenTitan, the OpenTitan port, as well as the FSP-based solutions for Oreboot.
Thanks, Ryan. So yeah, so the Oreboot also works with the OpenTitan. As you all know, OpenTitan is a RISC-V architecture design board. And OpenTitan is designed for embedded systems, so it's not a Linux capable. And so that's why we want to come up with an open source root design for the root of trust in the terms of both software and hardware implementation. Then you can find in the GitHub is over there. And while there's currently no ASIC available solution yet, the Oreboot also currently is run on the validator and it's also proven run on the FPGA, which is on the Intel Max 10. And so currently our work is also trying to put to Docker. You can refer to the earlier this year in the Global Summit, there's a talk on enabling OpenTitan with Oreboot on Intel FPGA. It will provide you much more details about how we implement it. So basically, we want to show that the Oreboot's simplicity, it suits the need for the embedded design in this case. And it's completely design from ground has a support for the RISC-V architecture. So next slide, please. Ryan? Yeah, okay. Yeah, so this is a quick preview to show that this is the Oreboot code structure for OpenTitan. So you can see that the left-hand side is pretty standard. There's architecture, CPU, SoC, the architecture folder, and then the virtual device folder, the physical device folder, is always under the mainboard folder. But on the right-hand side, you can see that the files are also pretty straightforward. There's a bootblock.s, which just do a simple early initialization code for the RISC-V. And then the bottom there's a link file and the main Rust file. So do a basic setup and then just pass the control to the payload. So that's it for the OpenTitan. Yeah, next slide. Okay, so now I also want to talk about how to enable the FSP on the Oreboot. So to enable on Intel platform, Intel provides a very easy solution. So it's compatible for all the bootloaders. So that's why you just need to take our FSP binary block it is available in our GitHub, Intel GitHub, in the FSP GitHub. You can just get the FSP from there and you can port it to your bootloader of choice. So the way we design for our boot is similar to how the core boot plus FSP model, just that is in the Rust code. And currently we are using the FSP API mode, which is the quite established standard across the bootloaders, which is Sling bootloader and Coreboot as well. So as we know, the Oreboot is natively run in 64-bit, while the FSP currently runs 32-bit boot. So that's why we need to address on this concern. Yeah, so and our current progress of work is that we want to make it work for the QEMU first. Then the next one we will make it work for the upsquare board, which is based on UpOLED. And these are the FSP 2.0 standard. That's what our current target. So we'll talk about the keys to how to deal with FSP. So it's quite simple, as that you have to call the API entry point. Later on in the next slide, I will show you that there's a diagram. Yeah, so you can see that as a find FSP header, that there's a tree, but FSP-T, FSP-M, and FSP-S. So FSP-T stands for FSP 10 RAM initialization, which is before our RAM is initialized. So we want to do the cache as RAM. So the FSP-M is doing the memory initialization, as you know. The FSP-S is doing the silicon code initialization. So by separating these FSP API into the three different stacks, so it enables the developers to call it in a more simplified way. So yeah, back to the previous slide. So you can see that it's just an API's entry point and the firmware calls to hand off to the OS at the end. And also there's a FSP info hops required for the information hands-on. Yeah. So next slide. Let's see. Okay. And this, so currently, okay, when we talk about the RAS, right? So FSP is designed in the C code and then includes the FSP headers file as well, which is required by the bootloader to call into the certain UPDs and pass the information to the FSP API. So that's why here we are providing a very simple way to convert the headers file, which is in C code, to the RAS format. As this one is designed by Ryan, so you can see all these are the FSP UPD headers UPDs. There's a FSPS, FSPN, UPD, and then with the script, with the currently script available in the Oreboot, we can just call the script and then just convert the C code to the RAS code in just a few commands away. So once it's converted, you can see all the UPDs are quite standard. It has no difference with the C code, and then you can just consume it as the way you use it in C. So this provides the user a very straightforward way and a more simple way for them to switch from the C environment to the RAS environment. Yeah, that's it. So I want to pass the time back to Ryan.
All right, so if you want to get involved, probably the best way is to join the Slack and join the Oreboot channel. We're very friendly. We have a number of contributors. You can find all the source code on GitHub. And of course, there's lots of things which have to be improved in the CI system. We still need kind of a verified boot model. We need a better SPI driver, etc. All right, thank you so much.